The title.
There's 1 more minute.
Well, this no.
If you look
The clocks are not synchronized.
Not exactly.
They are not synchronized.
No, they are not synchronized. No, it's already 1 minute after. Anyway, our last 2 talks in the last session. Thank you all for being here. Spreading in potentials random in space and time.
Okay, so first of all, I would like to thank the organizers for inviting me, and I would like to congratulate Leonid Pastor. I encountered a paper by him and Figotin when I entered the field of chaos. Just entered, there was a version of their version of solution, what is now called in the mathematical literature, mathematical physics literature, as the Maryland model, and it was completely a different approach. So it was in some way a welcome to the field of quantum chaos, was that paper. Now, and finally, I would like to thank the people that stayed here until the last moment to hear these talks. So I would basically, sorry about that. Okay, and now I will talk about spreading in potentials that are random in space and time. It's work that was done mostly by my student Evgeny Krivolapov. That is now a postdoc in Columbia University. We had collaboration with Michael Wilkinson when he was visiting the Technion, and we collaborated with Liad Levy and Moti Segev that were doing the experiments that basically were stimulated this work. And we enjoyed discussions with Tom Spencer at various stages that this work was done. So first of all, thank you for listening to it, because the DAE of Israel Letters was thinking that that is basically bad science, and in particular he would not approve also this conference, because it claims that if the average of the potential is 0, then the spreading will be ballistic, and there is nothing like Anderson localization, and therefore this work was rejected from Israel Letters. And so this is a person that is doing experiments. He's an experimentalist. He is doing experiment on incommensurate potentials, and now it's clear he doesn't understand what's the difference between incommensurate and random. But okay, but he doesn't think that this work is interesting at all. But I hope that I will convince you that that is wrong. But anyhow, it is not accepted to Israel Letters. So you don't have to read all this story, but what's written in red. So it's not clear to everyone in the scientific community that there is something like Anderson localization. Okay, so now we'll go to more serious stuff. So the outline of the talk is as follows. I will give the experimental motivation. Then I will develop a theory in 1 dimension. And the theory will be for spreading. And as physicists, we like to define universality classes. I will relate it to a phenomenon in chaos that is known as Cherenkov resonances. I connect it to the Fokker-Planck equation. Then we'll discuss stuff in more than 1 dimension. And then all my work will be in terms of particles. In the end, we will show that waves for high momentum are doing the same as expected. But it's something that has to be checked. So the experimental motivation, and that's basically optics. Now I will flip it through quickly, and that is basically what you are interested in basically in the paraaxial in the solution of the wave equation. Now assume that the variation of the potential in the propagation direction is weak. Then you can neglect from the second derivative of the potential. You can neglect the second derivative as long as the variation is on scales that are larger than the wavelength of light. And you write the electric field as a slowly varying part times a rapidly varying part, and you can write an equation for the slowly varying part, and it takes this form where z is the direction of propagation, and this is the perpendicular direction, and you have the variations of the index of refraction, and you can see that if you call A psi, basically it satisfies an equation like the Schrödinger equation. And here is given the whole analogy, and this was actually presented in the talks of Sasha Finkelstein and Dima Shepelyansky. So now, and you have seen this figure. So this figure is basically how you look at it in the laboratory. You basically, the blue regions are regions of high index of refraction. You inject the beam into one, and if this is periodic, you get ballistic spreading, and if they are random, you get localization. And you basically can measure what comes out from the other side of the crystal. So this is periodic. This is weak randomness, that you just get diffusion on that scale, and afterwards you get localization. And what is measured here is the inverse participation ratio, and what you basically see that the effective width decreases, and you see that you get here also the fluctuations of the inverse participation ratio, and you see the error bars are not errors, that are deviations between different samples. Now the reason that they are of the same size as the average is because, and this is just for the expert, I don't want to discuss it, because the dimensionless conductance is not large. It means it is small, it's 1.3. Otherwise they could not do the experiment. And this is a version that was also presented that is one-dimensional. You just manufacture it, and you see that for no disorder you have ballistic spreading, then you have diffusion, and then you get basically localization. As you increase the disorder, the length or the time is fixed. Now, and this is the version of atom optics, that you prepare a bunch of atoms somewhere. This tube is the one-dimensional potential. You let them spread, and you observe localization. So this is, so far, what was presented. The advantage of being in the place where the experimentalists are, that you hear from them what is the next paper that was not published yet. So this is what localization is. So this was the previous picture where you found localization. The way that you prepare it is that you make a diffuser, and the diffuser is basically something like Scotch tape, that you send the beam to it, but not everyone that uses Scotch tape in the experiment won the Nobel Prize. And then it passes through here. If you put it in the focal plane of the lens, you can, and this is a known trick of optics, you get on the other side of the lens the light that is a composition with Fourier components proportional to the points on the ring. So you can take each point as the propagation vector of each of them. So in this one, all of them will have the z component the same. So since the index of the change in the index of refraction is proportional to the electric field squared, what happens here is z independent. And that was a major jump in doing this experiment, because you wanted to make a potential that is random in the transverse direction, and this comes because each point is random. So for each Fourier component that comes out from each point here, you get something that has a different phase, but this is only in the perpendicular direction. What in the parallel direction, it comes is the same value of the wave number, and therefore it's uniform. Then they started to add to it to increase this ring. So now also kz, the propagation constant in the z direction, is varying, and therefore you have a potential depends on time, and it depends in a random way in time. And then you get spreading. Then they increased it more, and they get further spreading and further spreading, and this is free diffraction, as if there is no potential. So the spreading is faster than ballistic. So this is the puzzle of this experiment. How can we get spreading faster than ballistic in such an experiment? Now we reused, and it is some way, it would not be a great surprise if we would not grow up in condensed matter that we learned. And when you store Anderson localization, you get ordinary diffusion or Drude conductors. So now we try to look at the theory, and the theory we know only for particles. And so this was the puzzle, how to study something like this. Now for particles, something like this happens, and this we learned from Tom Spencer. In that time, Tom Spencer came to visit the Technion, and he drawn our attention to an old paper of an old paper of Rosenblut. Now, and the paper is just one page, and were the analysis of random potentials for particles, that the potential at random in space and time for particles were analyzed. And let me explain you now what is this theory. And so we are looking basically for particles, and let's assume the mass is 1 for simplicity, and we look at in the beginning in 1 dimension. And in 1 dimension will be most interesting. And this is the Hamiltonian, and basically the potential is of the form, is of this form, where an are independent random variables. The Fourier expansion coefficients are the coefficient of the Fourier expansion of random variables, and then we have phases. It depends on space and time, and if they are independent random variables, this is the meaning of it. That if you and they are of zero average, so you average of them, and now if you average two that are completely unrelated, this is what you get, and this is, and basically 1 and its Fourier complex conjugate. And as a simple example, you can take a constant times a phase, and the phase is uniformly distributed from 0 to 2 pi. And this fits what is done in the experiment. So in the experiment, that's an excellent approximation. And the sum in the experiment effectively has few thousand numbers. So this is the modeling of the experiment if it would be of particles. But the experiment is of waves, and I will comment on it in the end. So this is a well-defined problem in dynamics. So for each realization of the random potential, you have a chaotic system, and now you average over them. And now to connect it to what was mentioned in this conference, I think in the talk of Misha Sodin, this was called a Rademacher Fourier series, if it will be plus or minus 1, but this is more general. Okay. Now, how do we analyze this? How do we get some intuition what's going on? And this intuition is, we ask, where is the maximal resonance between the particle and the driving potential? And this is, in the context of chaos, this was the global picture that Chirikov had about chaos. So how chaos is formed? He would say, let's look when the potential is most effective in transferring energy to the particle. And that will be when the variation of this is small. And this, all of you know this phenomenon from the day of the kindergarten, because if you play with a swing, it's most effective to hit the swing when it stops, to be in resonance with the swing. Okay, so then we look what is the resonance of this. So we differentiate this, and we find this that this is the resonant velocity. And then we expand around this resonant velocity. So we subtract it, and this is in coordinates that move with this wave. And so each of the around each resonances, the motion is like of a pendulum of this amplitude, of this effective width. And then, so this is very easy to see. And now let's assume, let's see what happens if the amplitudes are small. So if the amplitudes are small, the resonances do not overlap. So you move in strips that are separated. Now, if you start outside of the resonance band, if the resonances live in a certain region, nothing happens. You just continue. You don't gain energy. Now the resonance starts to overlap, and you see a drift from resonance to resonance. And then you have a random walk between the resonances. And now let's analyze that random walk. So now now I will try to map it on a Fokker-Planck equation, and I will give you the conditions when I can make such a mapping. So then, this is of course related to decay of correlations. So the force is simply given by the derivative of the potential. And then what I have to do is I want to see how much the velocity increases. I have to integrate the force. And then, what is crucial is for statistics is the force-force correlation function. So if and it's a function of the positions and the times and the various times. Now, if the expansion coefficients are independent random variables, well, it is a sufficient condition, but it's not necessarily a necessary condition. It's not necessary condition. You find that the correlation function is basically translationally invariant and stationary. So it depends only on difference in position and time. And then now it's convenient to take a continuum limit, and the continuum limit is of course something that is an excellent approximation for the experiment that has thousands of these components. And we write basically the power spectrum that is the Fourier transform of this correlation function that takes this form. So basically S is the Fourier transform of the potential correlation function, and then therefore you have this k squared. Now you still see that there is a problem to work with this, because x1 and x2 are not just random variables, they depend on the times. They are point on the trajectory. And that so we need an additional approximation. And the additional approximation is that the force is weak, so the velocity doesn't change much. So I can assume that when the correlations are of reasonable size, the velocity is fixed. Then, from what you have seen in the previous slide, taking this quantity and squaring it and averaging over realizations, I get a diffusive process where the diffusion coefficient is given in terms of the basically the spectral content or the power spectrum of this. So basically, the power spectrum is what I need to do all the calculation. But as usually, the power spectrum is something that you have to calculate. In this case, in all these experiments, the power spectrum is something that the experimentalist has at hand. Therefore, it's so natural, because what it has in hand is because he has his lasers, and he basically designs his power spectrum. This is something that he designs. It's not something that he has to do much with it. So now what you see here, if the correlations fall off sufficiently fast, I extend the integral to infinity, and then I find the diffusion coefficient in terms of the power spectrum, and the Fokker-Planck equation for P, that is the probability density of the velocity, is given in this form in one dimension. And from this, I already can make some conclusions and find the various universality classes. So I mean, first thing I will do one dimension that's most interesting in this case. So I have to calculate the diffusion coefficient, and I ask what happens in the limit of very large velocity. I'm interested in the limit of large velocity. And this is the main universality class, and this was known, it's in the paper of Rosenbluth, but it was the way to calculate it, it doesn't give much of the derivation. It was known in the community, but it was not written in some way. Then, so we take the velocity to be very large, so we define a new variable, k prime, that is k times v, and then we want to take the limit of large velocity. So you scale through this equation, and you take s of 0, and then you find that basically the diffusion coefficient will go like 1 over the velocity cubed. And if this integral is something nice, not 0 and not divergent, you get basically, this is the result that you get. Now from this you can conclude a lot already, because you ask for a scaling solution of the Fokker-Planck equation. And counting powers, you can find that it's a function of the velocity only through this combination. What it means that the velocity q squared will grow like t to the 2/5. This will go like the velocity the velocity will go like time to 1 over 5. It's anomalous diffusion, and the space you just integrate it, and in space it will grow, and this is growth that is faster than ballistic. So this is an example how you can get from this growth that is faster than ballistic. So then, now, however, there is another universality class. And why there is another universality class is because so far, in the past, everyone assumed that this is a nice number, not 0 and not infinity. So it's just a constant, let's call it d0. But now, it can be, for example, 0. What will happen if it's 0? And this is something that happens in the experiment. Because when you look at this, what can happen is that that this is in some way bounded. And a typical case that it will be bounded is if you have a dispersion relation. So omega is k squared, that's something very natural, and k is bounded because this is the maximal wave number of the lasers. So then what will happen is that s of k and omega will be larger in this, will be basically 0 in this regime. You calculate the diffusion coefficient, you get a nice number of 0 for v larger than v maximum. And this was overlooked, but in experiments, this is typically what will happen in the end. But now there are also other possibilities. And the other possibilities, if you take the asymptotic expansion, what may happen is that this function has an essential singularity in 1 over the velocity. And this happens very often because this velocity is basically omega over k. And then what may happen is that you have a Gaussian beam. So in the variable 1 over v, it's an essential singularity. So all the derivatives with respect to 1 over v will vanish, and then this will eventually look like 1 over x or 1 over x squared. And this is very natural. This is basically a Gaussian beam in this. So Gaussian beams in momentum space are also possible. And then you can have cases where in the Taylor expansion of v, the first term will be will not be 1 over v cubed, but will be something higher. It cannot be lower than 1 over v cubed. But okay, so all this stuff the experimentalists can encounter. So now let's first check this theory so what we do is so the lines here are basically numerical simulations for various values of number of Fourier components, and the black line is the result of the Fokker-Planck approximation. And now what we did was also to change the force. So if the force is stronger, it is higher. So when the force goes to 0, you approach the Fokker-Planck limit. We could not get closer and finish the calculation in reasonable time. But there is no point, because we understand the point. It means that what the Fokker-Planck limit is. It's a limit of 0 force. And now, so there are important cases where there is dispersion relation, this I mentioned. Now in optics, the potential that you apply is slightly different. Because what you do is the electric field is given by such a Fourier expansion, and it's 0. But then the potential is basically given by the electric field squared, and it takes such a form. And then so this is just a technical difference. This is the potential, and then when you have to look at the different combinations of the Fourier components that do not vanish. This was done, and now I will present few simulations. How does it look? Now, something to warn when you compare with simulations is when you start with a sufficiently narrow distribution of initial conditions, so that you have a lot of chaotic systems, but for some time on some distance, the variations of the potential will not be observed, because for a short time everything looks uniform. So for a sufficiently short time, in each realization, the particle will follow acceleration, and then the velocity will increase with time. So then, and only afterwards, it will start to diffuse. Now, but if it accelerates in each realization, if you average the energy over of the realizations, you still see acceleration. So this is what you will see now. So what we see here is a potential that is we use a potential that is very similar to the one that they use in optics. Uniform distribution of wave numbers up to a certain region. So take a disk as use the disk as a diffuser, and then what you see is first you see that you accelerate, because up to some point the particles do not realize that the potential is random. There is some place in the potential. Then the black line is the solution of the Fokker-Planck equation. So you join the solution of the Fokker-Planck equation, and you follow the solution of the Fokker-Planck equation, that here it levels off, because this is a case that the spectral, the power spectrum does not have components with high velocity. So the velocity is here the ratio between omega and k, between the frequency and the wave number, and that is very special to optics. And this is what happens in real space. In real space, it is just the integration. It doesn't have really any special significance. Now, this is, instead of the uniform, it's a Gaussian. So again, you see acceleration. Then you join the Fokker-Planck, but the Fokker-Planck does not saturate now. It grows with what happened if a diffusion coefficient is a Gaussian of the velocity. And that is practically for large velocities, it's also a truncation. So then, and now remember, in this case and the previous case, there are regions where you are here that the diffusion coefficient, so this is a growth, this is the log of the velocity squared. So here the velocity squared is basically going linear with time. So this is a region where the diffusion coefficient in velocity is fixed. And so and remember it, it will be important for the experiments afterwards. Okay, now we go to a dimension that's higher than 1. For a dimension that's higher than 1, from the Cherenkov condition, we get basically the condition instead of v times k is omega, it's v dot k is omega. And that's very important because it can be satisfied even if k and omega are bounded. You just play with the angle. And then the integral for the diffusion coefficient takes this form. There's a scalar product here, there's a scalar product here, and there is a scalar product here. And when we do this integral, it basically integrates out all singularities and all essential singularities. And basically, even if omega and k are bounded, the velocity can be, there are solutions with unbounded velocity. And then this is the Fokker-Planck equation. When you scale the Fokker-Planck equation through, you still find that v squared, but grows like t to the 2/5, but there are no other universality classes because you have this integral. So this is now the only universality class. The growth in position is not the integral of this. It is t squared. It is v squared goes like t squared because most of the time the velocity increases in a direction that's perpendicular to the velocity. So although the velocity increases, it does not spread too much in space. But the point is that in higher dimension, you don't have any other universality classes. And so this is the Gaussian, and you compare it with the Fokker-Planck, it matches. The one line is a simulation. Now what you do is, now this is the potential that used in optics in this experiment. So basically, again, the particle will go like this. Then it will join the Fokker-Planck, but it will not stop because the velocity, the diffusion coefficient, now goes continues to go like 1 over v cubed, and the velocity goes like the velocity squared goes like t to the 2 over 5, 2 with the exponent of 2/5, and again here there is a region where you see a fixed diffusion coefficient, and the diffusion velocity will not stop for higher dimensions, but the spreading in space goes like ballistic. It goes like x squared. Again, but now this is asymptotic. But in this region, so it might look in a different way. So now, so this was so far, everything was for particles. Now the experiment is for waves. So come the question of comparison. Now we expect that if you ask about spreading, in the end it has to go to high momentum. High momentum is short wavelength, and there is correspondence. But then we decided that we want to check it. So what you find here, this is the boundary of the Cherenkov box. So above this line, there are no Cherenkov resonances. The dashed line is what would be the average of the velocity if it spreads uniformly in the Cherenkov box. The blue is a simulation for particles. The red is the simulation for waves. And you see they quite agree with what they are doing in the end. Now, this is the probability distribution for particles and waves. You started somewhere in the center. These are the limits of the Cherenkov box, where there are Cherenkov resonances. Here there are not Cherenkov resonances. So you see the particles are just filling the box in some way, and there is a small spread out. This is what I told you, that you may get out because the force is not zero. But then for the waves will tunnel out and fall off exponentially, like you expect for waves. This is a logarithmic scale. Now, if you start outside of the Cherenkov box, in a region where there are not Cherenkov resonances, so what you find that nothing happens, neither for the particles or for the waves. It means they get stuck. There is no resonance, and there is no magic for it. Then this is the probability distribution. This is where the Cherenkov box is, where the resonances are, and here is where you start. Nothing happens. So now if you bring this point closer and you start to, from here, I didn't want to put too many figures, then what you get, the particles get stuck, the waves can tunnel through, and so on, as we expect for waves. But they will not go very far. Okay, so this is now the summaries. Well, we got a formula for the diffusion coefficient in terms of the we got a formula for diffusion coefficient in terms of the Fourier components, and this is, there are hints of such formulas, but we didn't see it in a clear way. And the reason that was natural for us to develop it is because the experimentalists were doing it. And now we classified universality classes. The main class was known before with the 2/5. The other classes, so we have other classes again. We found them just because this is what's natural for this experiment. And then we found initially uniform acceleration for narrow wave packets, and asymptotically the behavior of particles agrees with the one of waves. Now the relation with experiments. In experiments, they observed hypertransport that is faster than ballistic. Now this is something that you can really have, after you think a bit, it's not a great surprise, because your potential depends on time. The energy is not conserved, but the point is that you get it faster in some way. You get the velocity increasing. The way that it looks, unless we find something else, it looks that this is just a result of having the experiment in the region where the diffusion coefficient in velocity is constant. So if the diffusion in velocity is constant, then basically the velocity will go like root of t, and the position, the spreading in position, will be like t to the 3/2. But it means, but this is a narrow region. Now the question, if all this is correct for waves and 2 dimensions, this is something that we still want to look. And the question is how we increase in the experiment the region where you get basically this diffusion in velocity. It's not be such a narrow region. So this is something we're thinking. The open problems are identification of the regimes where the Fokker-Planck equation fails, and how to analyze these regimes. So how we correct the Fokker-Planck and how we go beyond Fokker-Planck for particles. Then we want a more analytic theory for spreading in coordinate space. And then it would be nice to find a regime where particles, for high momentum, where particles and waves behave in a different way. So it's more interesting than all of what I was telling you. But so far we did not find, and we try to look if it's possible. And so this is one of the main questions. And of course, experimentalists are very interested in this question. So thank you very much.
Questions?
Where will your paper appear?
Pardon?
Where will your paper appear?
PRE, rapid communication. Now the long version of it, a long version of part of it, appeared in the New Journal of Physics. And that was accepted very quickly. Now it will appear in rapid communication. It's a different version, and all of this is on the archive, of course. So it's an archive, and if some of you really want to find it very quickly, you can look at my website.
Other questions?
Well, maybe someone has comments.
Well, if not, let us thank the speaker again.